Hello friends, myself Dr. Nandakumar Rao from College of Engineering Ambazogai is going to deal with Applied Thermodynamics 1. This is our 14th lecture. So in previous lecture we have discussed about combustion equations on the basis of mass analysis as well as on the basis of volume analysis, which help us to determine the quantity of oxygen required to burn constituent of fuels such as carbon, hydrogen, sulfur, etc. So today we will discuss about the flue gas analysis by mass, then flue gas analysis by volume, and minimum air required per kg of fuel to be burned. So today we will see how the analysis, gravimetric analysis, that is nothing but the mass analysis, is converted into volumetric analysis and vice versa. So here the equal molecular mass of all gases occupy the same volume at a given temperature and pressure. So whatsoever may be the gas having equal molecular mass and same temperature and pressure used to occupy same volume. Now second thing is the proportional volume of constituent gas multiplied by molecular mass of constituent gas will give proportional mass of constituent. So here if we want to find out the proportional volume is known, volume analysis is known to us, then for each constituent of gas, say for example the flue gas is collected and the analysis is made, and from that analysis we obtain the idea about the percentage of carbon dioxide present in the flue gases on the volume basis. So if this volume is multiplied by molecular mass of constituent gas, then it will give proportional mass of that constituent gas. Proportional mass of that constituent gas can be obtained. That is nothing but the volumetric analysis can be converted into gravimetric analysis by multiplying it by molecular mass of that constituent gas. And second thing is reverse of that is also possible. So if we know proportional mass of constituent gas, that is mass analysis is known, then reverse of previous thing, here we do multiplication in first case, in second case we divide it by molecular mass, then we will get proportional volume of constituent gas. So mass analysis can be converted into volume analysis, or volume analysis can be converted into gas analysis. So in first case volume analysis, if it is multiplied by molecular mass, then mass analysis is converted into volumetric analysis is converted into mass analysis or gravimetric analysis. And if we know gravimetric analysis or mass analysis, then dividing gravimetric analysis by molecular mass will give proportional volume of constituent gas, that is volumetric analysis can be obtained. Now coming to this conversion of volumetric analysis to gravimetric analysis. So if we know volumetric analysis of sample of flue gases as given below. So for example, the gas contains flue gas contains 10.5% of carbon dioxide by volume. This analysis is given on the volumetric basis. Then second thing, the gas contains carbon monoxide, that is 0.5%. This is the analysis. Some gas coming out of combustion is collected and analysis is made, and it is found that that gas contains 10.5% of carbon dioxide on the volume basis, and carbon monoxide, that is 0.5 on volume basis. Then oxygen, flue gas also contains oxygen by 8%, that is 8% of oxygen is present. Next one is nitrogen, it contains 81.0% nitrogen by volume. Then it is asked for us to determine gravimetric composition of flue gases. So this composition which is given is on the basis of volume. So we call this as a volumetric analysis. This volumetric analysis can be converted into gravimetric analysis. That is, gravimetric analysis is nothing but mass analysis, and vice versa. So how to convert it into gravimetric analysis that we see. So here we have to form this table. So in this table we have to write constituent gas, volumetric analysis, molecular mass, and proportional mass, and gravimetric analysis. So in this last column we get gravimetric analysis. So we'll take the given data one by one. So in this, carbon dioxide is 10.5%. So we take here carbon dioxide is 10.2%, sorry, 10.5%. This is 10.5. Molecular mass of carbon dioxide, molecular mass of oxygen is 32 plus 12. 32 plus 12 is 44. Molecular mass of carbon dioxide is 44. 44 into 10.5 gives us 462. Then second constituent is carbon monoxide, 0.5%. Here we write carbon monoxide CO, 0.5%, and molecular mass of carbon monoxide is 12 plus 16, that is 28. 12 is molecular mass of carbon, and oxygen is 16. 16 plus 12, 28. So multiplying 0.5 to 28 we get as 14. The next constituent given is oxygen, O2. Constituent of gas on volume basis, oxygen is 8%. So here molecular mass of oxygen is 32. 8 into 32, this works out to be 256. Then next constituent is nitrogen, which is 81%. So we take 81%. Sorry, here we have to write constituent. So here constituent is nitrogen, which is 81% by volume, and molecular mass of nitrogen is 28, and this works out to be 2268 is proportional mass. Now adding all these proportional masses, we get summation of C as 3000. Now gravimetric analysis we can find out. So here C divided by summation of C, C value is 462, divided by summation of C is 3000 into 100. This works out to be 15.4%. So here carbon dioxide on mass basis is 15.4, on volume basis it is 10.4. So here carbon monoxide 14 divided by 3000 into 100. On simplification it works out to be 0.466. So carbon monoxide is 0.5% by volume, whereas by mass it is 0.466%. So oxygen 256 divided by 3000 into 100, which works out to be 8.533%, whereas nitrogen 2268 divided by 3000 into 100, which is equal to 75.6%. And if we add 15%, 0.4%, 8%, and 75%, this works out to be 100%. So here, this is given on the volume basis. The constituent gas carbon dioxide by volume it is 10.5%, whereas on mass basis it is 15.4%. Carbon monoxide is 0.5% by volume, whereas it is 0.466% by mass. Oxygen present in the flue gas is 8%, whereas on mass basis oxygen percent is 8.533%. Nitrogen present in the flue gases on volumetric basis is 81%, whereas on mass basis it is 75.6%. So this is how we convert volumetric analysis only to the gravimetric analysis or mass analysis. So now coming to conversion of gravimetric analysis into volumetric analysis reverse. The percentage analysis by mass of sample of flue gas is given as below. Some gas is collected and the analysis of flue gas is made on the basis of mass. So this is nothing but we call as a gravimetric analysis. So what it contains on the basis of mass. So carbon dioxide is 16%. The next one is carbon monoxide 0.95%. Next one is oxygen 7.60%, and nitrogen is 75.45% by mass. And it is asked to us determine volumetric analysis of composition of flue gases. So mass analysis is given, that is to be converted into volumetric analysis. How to convert this mass analysis or gravimetric analysis into volume analysis, that we see. So again here first constituent is carbon dioxide as given here. So carbon dioxide is 16%, so we write here 16%. And molecular mass of carbon dioxide is, we know that is 44. So here C divided by A, C is equal to A divided by B, so that is 16 divided by 44, which works out to be 0.3636. So now second constituent is carbon monoxide 0.95, so CO 0.95. So this is conversion of mass analysis into volumetric. It is reverse of previous case. So carbon monoxide is weight is 28, so 28.95 divided by 28, which works out to be 0.0339. Then next constituent is oxygen 7.60%. Oxygen 7.6%. Molecular mass of oxygen is 32. 7.6 divided by 32. This works out to be 0.2375. And next constituent is nitrogen 75.45. Nitrogen 75.45. Molecular mass is 28. 75.45 divided by 28, which works out to be 2.69, 2.6946. So now summation of this C, if we find summation, this works out to be 3.3296. So conversion to the volumetric analysis is again in percentage, volumetric analysis in percentage. So D is equal to C divided by summation of C. C value is 0.3636. Summation of C is 3.3296. So this works out as 10.92%. The next one is carbon monoxide, 0.0339. This 0.0339 is value of C. Summation of C is 3.3296. This is equal to into 100. This has to be multiplied by 100. Has to be multiplied by 100. So this works out to be 1.018%. So again, oxygen 0.2375 divided by 0.3296 into 100. This works out 7.184%. Again, percentage of nitrogen 2.6946 divided by 3.3296. So this value is taken here. This value is in the denominator, C value in numerator, summation of C in denominator into 100, which works out to be 80.928. So if we add 10.92%, 1.018%, 7.18%, and 80.92%, this works out 100%. So this is how a carbon dioxide which was obtained on the mass basis 16%, percentage was 16. So here on volume basis it is 10.92%. Carbon monoxide was 0.95% on mass basis gravimetric analysis, and on volume basis it is 1.018%. Oxygen was 7.6% on gravimetric analysis, but on volumetric analysis we obtained it as 7.184, and nitrogen was 75.45% on gravimetric basis analysis. On volumetric base it is 80.92%. So this is how we convert the gravimetric analysis into volumetric analysis, and in previous case we have seen the conversion of volumetric analysis into gravimetric analysis. This is also in percentage, gravimetric analysis in percentage we can say. So conversion of volumetric analysis to gravimetric analysis and conversion of gravimetric analysis to volumetric analysis, here we have studied. So now coming to the constraints of fuel and minimum quantity of air required, oxygen required, that we will see. So every fuel contains some kind of constraints which undergo the combustion process and produce the heat. So here let the fuel have following constraints. So fuel will have different kind of constraints which are capable of burning and producing heat energy. The very first constraint is carbon. C, let the C be the parts by mass of carbon in the fuel. So if C is the quantity of carbon present in the mass of fuel, then H2 be the parts by mass of hydrogen. A fuel contains hydrogen, and H2 is the parts by mass of hydrogen. Then O2 is the parts by mass of oxygen. Oxygen sometimes is present in the fuel, and that is considered. That does not produce any heat energy. Oxygen does not produce any heat energy, but it reduces the amount of oxygen required for combustion, because already fuel contains oxygen. So some quantity of oxygen required from air is going to get reduced, and S is the parts by mass of a sulfur. So these are the major constraints which help in combustion of fuel and producing heat energy. Now, oxygen required per kg of fuel constituent that we want to find out. So here, the fuel constituent required some sort of oxygen for combustion in different quantity as given below. So in previous class, we have seen the combustion equations, and in that combustion equation, quantity of oxygen required was discussed. So here, if we want to burn C kg of carbon, it requires C into 8 by 3 kg of oxygen. So this we have discussed in previous class. C kg of carbon requires C into 8 by 3 kg of oxygen. So this is one. Then if we want to burn hydrogen, it requires H into 8 kg of oxygen. And if we want to burn S kg of sulfur, it requires S into 1 kg of oxygen. And if oxygen is present already in the fuel, then quantity of oxygen required can be reduced by the quantity of oxygen present in the, so this is subtracted. So now oxygen required for complete combustion. So here already we have seen, say for example, some fuel contains carbon, hydrogen and sulfur in it. So if it contains carbon, it requires C into 8 by 3 kg of oxygen. If it contains hydrogen, it requires H into 8 kg of oxygen. If it contains sulfur, then it requires S into 1 kg of oxygen. So these number 1, number 2, number 3 add together, whereas number 4, percentage of oxygen present in the fuel reduces. So number 4 is subtracted. So now we will see how this oxygen required for complete combustion is calculated. So oxygen required for complete combustion of 1 kg of fuel. So here mass of fuel is considered as 1 kg. So if 1 kg of fuel is taken and that fuel contains carbon, hydrogen, nitrogen, oxygen present in the fuel. So how much quantity of oxygen is required per constituent of fuel that we see here. So say for example, 1 kg of fuel is taken, out of that C grams, we can say C grams, or in fraction we can write C kg of carbon is present in 1 kg of fuel. Say for example, if we take 1 kg of fuel, it contains 800 grams of carbon. So that 800 grams is percentage of carbon or mass of carbon present in the fuel. Then H2 is the mass of hydrogen. Say for example, 100 grams is the mass of hydrogen. So H2 is 100 grams. Then remaining is, say for example, sulfur. Sulfur is say 100 grams. So 150 grams. Sulfur is 150 grams. H2. So this is nothing but composition. And oxygen is also present, and that is 50 grams, that is 0.05 grams of oxygen is present in the fuel. So these are the constraints. So if we want to find out oxygen, then so 8 by 3 into C is the mass of oxygen required to burn carbon. 8 into H2 is the mass of oxygen required to burn hydrogen. S into 1 is the mass of oxygen required to burn sulfur, and minus O. So already this whatsoever oxygen is required for these three constituents is taken from air by subtracting this percentage of oxygen present in the fuel. So say for example 50 grams is already present, and total if we want 2 kg of oxygen, out of that 50 grams is subtracted, remaining oxygen is taken from air. So this amount of oxygen required is 2 in minus of 0.05. So that much amount of, so here this is not in grams, this is in kg. 800 800 gram means 0.8 kg, 100 gram means 0.1 kg, 150 gram means 0.15 kg. So this is in kg. 50 grams is nothing but 0.5 kg. 150 grams is 0.15 kg. So now here 2 kg is required actually to burn this fuel for carbon, hydrogen and sulfur. So already oxygen is present in the fuel, that is subtracted. 2 minus 0.05 kg of oxygen is required, say for example. So now we will see here by rearranging this above equation. So 8 by 3 into C is taken as it is, 8 is taken common, H2 minus O2, 8 is taken common, therefore O2 is divided by 2, this is taken into bracket, plus S, S is taken as it is. So only these two terms O2 and H2 are combined in a bracket by taking 8 as common factor. So this is nothing but amount of oxygen required for complete combustion of fuel. So now this oxygen is taken from air. So air contains oxygen and that oxygen is to be extracted for combustion. How much of air is required for combustion, that we have to find out. Minimum quantity of air, minimum air required for complete combustion of fuel. So here if we say atmospheric air contains 23% of oxygen by weight, the rest of the thing is 77% are other constituents which are present in the air by mass. So 23% is the only oxygen. If we want quantity of oxygen, so how much of air is required? 1 kg of air contains only 23% of oxygen, that is nothing but 230 grams of oxygen is present. And if we are in need of 1 kg of oxygen, then we have to take much of the air so that the requirement can be fulfilled. So how to find out that amount of air required? So 100 divided by 23 kg of air, 100 by 23 kg of air is required to have 1 kg of oxygen. If we want 1 kg of oxygen, 100 by 23 kg of air is to be taken, then we get 1 kg of oxygen. So now minimum air required per kg of fuel is obtained like this. So here the equation which we had earlier obtained as 8 by 3C plus 8H2 minus of O2 divided by 8 plus S. So that is multiplied by 100 divided by 23. So this is nothing but amount of oxygen. So whatsoever may be the quantity of oxygen required, that is multiplied by 100 by 23. If we want 1 kg, then 100 by 23. If we want 2 kg, then we have to multiply 2 into 100 by 23. So that much of air is required. So this equation which we have obtained earlier is multiplied by 100 by 23, that gives us minimum quantity of air required. So on simplification, these constants, after simplification we get 11.6 C plus of 34.8 H2 as it is, O2 divided by 8 and S into 100 divided by 23, that gives us 4.35 S. So this is say equation number 2. So this equation number 2 gives us minimum amount of air required for complete combustion of 1 kg of fuel. So now coming to next, we will solve one numerical. So there is one problem. Problem is defined like this, explained like this. A sample of coal has following percentage of composition by mass. So fuel analysis is made and the constituents of fuel are analyzed and those constituents are explained as given below. So now first constituent of fuel is carbon. Fuel contains carbon by 77% by mass. The next one is fuel contains hydrogen, it is 6.8%. Then fuel contains nitrogen and that is 1.20%. And sulfur is also present in the fuel, is 2.20% by mass. and oxygen is present, that is 8.8%, and incombustible, that is the contents like ash which are not capable of burning, are 3.30% by mass. So here it is asked, determine minimum quantity of air required. So how much of air is required to complete combustion of 1 kg of coal, and constituent products. So what are the constituent products of flue gas? So what the flue gas contains on the mass basis, that we have to find out. So here to find this we have to prepare a table. So first one is fuel constituent, then mass per kg of coal, then oxygen required to burn this fuel constituent, and then oxygen required per kg of fuel, then product of combustion, carbon dioxide, hydrogen, water, sulfur dioxide and nitrogen present in the flue gases. So flue gas analysis can also be obtained here. So we'll solve this one by one. Coming to first, carbon is 77%. So here C, carbon is 77% by mass. So 77%, if we are here, it is explained about 1 kg of fuel. So if we take 1 kg of fuel, 77% is the carbon, means it contains 0.777 kg of carbon. So this requires 8 by 3 times of carbon as oxygen, 8 by 3 into C. So 8 by 3 into 0.77 gives us A into B, 8 by 3 into C. So this is, oxygen is required 8 by 3. So 8 by 3 into C, 8 by 3 into 0.77. This works out 2.072 kg of oxygen is required. So second constraint of fuel is hydrogen. Hydrogen is 6.80%. So H2, hydrogen is present in the fuel, and that is 6.82%, means 0.068%, and hydrogen requires 8 kg of oxygen to burn, and if we multiply A and B, so then we get this as 0.068 into 8. This works out to be 0.544 kg of oxygen is required. The next constituent is nitrogen. Nitrogen is 1.20%. N2 is present in the fuel. 1.20 means it is 0.012, and this is not burned. So here oxygen is not required. So this does not require any oxygen here to burn this. Then next constituent is sulfur, 2.2%. So sulfur is 2.2%, means this is 0.022. So this sulfur requires 1 kg of oxygen. So total oxygen required is 0.022 into 1, which is equal to 0.022 kg. So these numbers 8 by 3, 8, 1, that we are writing from combustion equations which we have studied in previous class. So oxygen is present in the fuel. How much of oxygen is present? 8.8%. 8.8% means 0.088. So this does not require to burn oxygen. We need not to have a oxygen. So actually oxygen, this oxygen itself helps to burn the fuel. So -1 is the oxygen required. So this much of oxygen is already present, and that oxygen we have to subtract from the total required oxygen. Therefore this is taken as -1. So here we get -0.088, and then afterwards we have the incombustible product, that is 3.03%. So 3 point, we can call this as ash, say, incombustible, and this is having percentage of 3.3%, so 0.033, and does not require any oxygen, so does not require any kind of oxygen, does not produce carbon dioxide, water, sulfur, nitrogen, nothing is produced. So here what we are going to get is, so total oxygen required to burn carbon is 2.07 kg. To burn hydrogen we need 0.544 kg, and to burn sulfur we need 0.02 kg of oxygen, and to burn oxygen we need oxygen, this 0.088% kg of oxygen is additional that we can subtract. So now here products of combustion, so by burning 0.777 kg of carbon we can produce carbon dioxide, and that carbon dioxide is produced is 11 by 3 kg. So in previous lecture we have seen, by combustion of carbon in presence of oxygen produces CO2. So here this carbon dioxide which is produced is 11 by 3 kg. If we burn 1 kg of oxygen, then we produce 11 by 3 kg of carbon dioxide. So multiplying this 11 by 3 with 0.77, if we burn 1 kg, then it is producing 11 by 3. If it is burned 0.77, so here 0.777 into 11 by 3, so carbon dioxide produced is 2.849 kg, 2.849 kg. So when we burn carbon, so it does not produce hydrogen, it does not produce water, it does not produce sulfur dioxide, does not produce nitrogen. So when we burn hydrogen, it produces water, it does not produce carbon dioxide, sulfur dioxide and nitrogen. So here to produce this water, so here combustion of 1 kg of hydrogen in presence of 8 kg of oxygen produces 9 kg of water. So 9 into, this is multiplied by 9 into 0.068, so this produces 0.612 kg, 0.612 kg of water is produced. And then on combustion of nitrogen, so it does not produce carbon dioxide, does not produce water, it does not produce sulfur dioxide, and same nitrogen is coming out as 0.012. Then on combustion of sulfur, does not produce carbon dioxide, does not produce water, but it produces sulfur dioxide. So by combustion of 1 kg of sulfur in presence of 1 kg of oxygen produces 2 kg of sulfur. So here sulfur dioxide, so here we have to multiply it by 2 into 0.022, so this produces 0.044 kg of sulfur dioxide, and no nitrogen is produced by combustion of sulfur. So oxygen is burned, and this oxygen does not produce carbon dioxide, hydrogen, sulfur dioxide and nitrogen. So now looking into this, here if we find out summation of C, so this is nothing but 2.55 kg of oxygen is required completely to burn carbon, to burn hydrogen, to burn sulfur. So we need 2.55 kg of oxygen. So if this much of oxygen is required, then how much of air is required, that we can calculate. So here, therefore, minimum air required for complete combustion of 1 kg of given fuel. With the constraints as I explained, here we need 2.55 kg of oxygen, and to have 2.55 kg of oxygen we have to multiply it by 100 divided by 23. If we want 1 kg, then 1 into 100 by 23. If we want 2 kg, then 2 into 100 divided by 23. So if we want 2.55 kg, 2.55 kg of oxygen into 100 divided by 23 gives us 11.086 kg of air per kg of fuel. So this can be obtained by another way also. That another way is, already we have derived one formula. That formula is minimum amount of minimum air required in kg per kg of fuel is given by one equation. That equation was 11.6 into C plus 34.8 bracket H2 minus O2 divided by 8 plus 4.35 sulfur. So in this problem itself it is given carbon percentage 11.6 into 0.777 is percentage of carbon plus 34.8 into percentage of hydrogen given in this problem is 6.8%, that is 0.068 minus percentage of oxygen is given as 8.8% means 0.088 divided by 8 plus 4.35 into percentage of sulfur is 2.2%, that is nothing but 0.022. On simplification again this works out to be 11.086 kg of air per kg of fuel burned. So directly we can find out minimum air required using this formula, or else we can find out minimum air required by using this previous table. So by previous table we can find out minimum amount of oxygen required, and multiplying this minimum oxygen by 100 divided by 23 we get mass of air required for combustion. Or directly we can use this equation to find out minimum air required. This is second method. Along with that, he has asked us to find out the composition of flue gases. So to find out composition of flue gases, so carbon dioxide produced, CO2 produced, can be obtained like this. So here carbon, mass of carbon is known, carbon into 11 by 3 kg. If we burn 1 kg of carbon, it produces 11 by 3 kg of carbon dioxide. So C into 11 by 3 is nothing but 0.777 into 11 by 3. This gives us 2.849 kg of CO2 is produced. Then second one is water, H2O produced. H2O produced can be obtained as 9 into percentage of H2. So 9 percentage of H2 is known, that is 0.06. It actually percentage is 6.8%. So 0.068. So multiplying this, we get it as 0.612 kg of water H2O or steam is produced in the combustion of fuel. So next constituent of this gas is sulfur dioxide, SO2 produced. If we burn 1 kg of sulfur in presence of 1 kg of oxygen, it produces 2 kg of sulfur dioxide. So 2 into S. So 2 into percentage of sulfur given is 2.2%, means 0.022. So this works out to be 0.044 kg of SO2 sulfur dioxide is produced, and the nitrogen which is present is directly transferred as it is. The nitrogen present is 0.012 kg, or that is 1.2%. So 0.012 kg of nitrogen N2 is present in the flue gases on combustion of 1 kg of fuel. So all this data can be obtained by simple method. We have seen two methods. One is a tabular method. In this tabular method, we have obtained mass of carbon dioxide, mass of hydrogen, mass of nitrogen, mass of sulfur dioxide, and then we obtain minimum quantity of air required by using tabular method. Simple by using equation also we can find out mass of minimum mass of air required for combustion of 1 kg of fuel, and similarly we obtain the constituents of flue gases on mass basis. So this is on mass basis. So whatsoever is the total mass of flue gases produced, out of that, so this is 2.849 kg of carbon dioxide. So total gases, if we see 2.849 kg of carbon dioxide, then 0.612 kg of water, then 0.044 kg of sulfur dioxide, and nitrogen is also present, 0.012. So adding together, total mass of gas produced is 9 plus 2 11, 15 plus 2 17 plus 1 carry, 5 plus 1 6 7 7 plus 4 11 11 14 15 carry 1 3.157 kg of flue gas is produced. On percentage, if we want to find out percentage of carbon dioxide on mass basis, is obtained as, so 2.849 divided by 3.517 is into 100 is percentage of carbon dioxide on mass basis. Then H2O water produced is 0.612 divided by 3.517 into 100. This is also in percentage. Sulfur dioxide produced. Flue gas analysis on mass basis can be obtained here. 0.044 divided by 3.517 into 100%, and then nitrogen in the flue gases is 0.012 divided by 3.517 into 100%. So this gives us the flue gas on the basis of flue gas analysis on the basis of mass. So let us see calculations like this. So 2.849 divided by 3.517 works out to be 81%. 81%, 1.00% is carbon dioxide, then 0.612 divided by 3.517. This is 17%. 17.4% is water, and sulfur dioxide 0.044 divided by 3.517. So this produces sulfur dioxide as 1.25% and 0.012 divided by 3.517. So this produces 0.34%. 0.34% is the percentage of nitrogen. 0.34% is the nitrogen in the flue gas. So this we can call as mass analysis of flue gases in percentage. So earlier we obtained the exact mass of constituents in flue gases. So if we want to convert that into the mass analysis, then mass divided by total mass of flue gas into 100 gives us percentage of carbon dioxide on the mass basis in the flue gas is 81%. So in this way we can find out mass analysis of flue gases also, and this mass analysis can be converted into volume analysis that already we have studied. So for today this much is sufficient. I hope you followed the things. So in next class we will continue.